Hello Lama. Let's start the session for today. Today we are going to discuss about the rest of the reactions with these block metals. Right? Last day we had discussed about how these block metals will react with O2 gas as well as with N2 gas. Right? Today we are going to start our discussion with these metals reactions with H2 gas. Right? Let's discuss how these S block guys will react with the hydrogen gas. Right? Okay. So first we are going to discuss about the reactions with H2 gas. Reactions with H2 gas. Right. When it comes to reactions with H2 gas, Lamai, other than the beryllium, it is the least reactive out of S block elements. Other than that, all the other elements of S block will react with H2 gas. Basically, when reacting with H2 gas, we are supposed to come up with the hydrides. If S block gas reacts with O2 gas, those will produce the oxides, the oxygens, monoatomic anionic form, the O2 minus. When they react with N2 gas, they will come up as nitrides, the nitrogens, monoatomic form, the N3 minus. Like that, when S block guys react with H2 gas, those will come up as hydrides, the hydrogens, monoatomic anion, the hydride. Always when it comes to monoatomic anions formed by these nonmetals, those will always come up with the nearest noble gas configuration, the next noble gas configuration. See, when it comes to oxide, the oxygen is with 8 electrons, the next noble gas coming up with 10 electrons, the neon. So it needs 2 electrons to achieve that configuration. So oxide is the O2 minus form. Oxide coming up as O2 minus. So when it comes to nitrogen, this is 7 electrons. Right, the next nearest noble gas is neon, which is 10 electrons. So to come up with the nitride, you need 3 electrons. Right, that is why the N3 minus is formed. The monoatomic anionic form always coming up with the noble gas configurations. So when it comes to hydrogen, hydrogen's nearest noble gas is the helium. So to come up with the helium configuration, hydrogen need 1 more electron. That is why the hydride is referred to as the H minus. So these two guys, other than beryllium, will form the hydrides. Right? So all these two guys, other than beryllium, right? So when it comes to lithium, right, it will react with the H2 gas and forms the lithium's hydride, right? So the balancing is very easy, right? Not that much of thing to do with the balancing. Two of this, right? Sodium, potassium, rubidium, cesium. Over the group 1 guys. React with H2 gas to form the respective hydride, right? So normally you need to heat this stuff, right? To come up with the hydrates. So 2 of sodium hydride will be produced, right? So for potassium, for rubidium, as well as for cesium. All the group 1s will produce the hydrates with H2 gas, right? As well as the group 2s, other than beryllium. right? Beryllium won't produce the hydride in normal conditions, right? You can see no reaction there. Other than beryllium, rest magnesium, calcium, strontium, and barium all will produce their respective hydrides, the H-4. Right? Magnesium's hydride. Exchange of valence is Mg2 plus, right? H minus. So hydride coming up as this CaH2, strontium hydride, and barium hydride. Right? When we are discussing about the special things with these hydrides, the major special thing is all of these hydrides, these block hydrides other than the beryllium, so beryllium won't form normally, are considered as ionic hydrides. All of these are considered as ionic hydrides. That is very special. Nah? All of these is block hydrides are considered as ionic hydrides. See, referred to as ionic hydrides. Right? Ionic hydrides. Even these. Other than beryllium, the S block hydrides are referred to as ionic hydrides. This is very special, huh? Considering these guys as ionic hydrides is kind of a special thing. Why is that? The thing is this, Lama. Right? Thing is this. Basically, when it comes to electronegativity difference, between the S block metal and the hydrogen is not going to be equal to or greater than to 2. But normally what we know is, right, what we know is when the electronegativity difference is greater than 2, then we consider the compound as ionic or bonds as ionic. So if the electronegativity difference is less than 1.7, then the bonds are considered as covalent normally. That is a normal scenario to come up with whether the bond between two atoms are covalent or ionic. But when it comes to these S block hydrides, the electronegativity difference is actually less than 1.7. Less than 1.7. So hydrogen's electronegativity is 2.1. Hydrogen's electronegativity is 2.1. Right? When it comes to S block elements, the smallest value available with the cesium, which is 0.7, one can see this 0.7, 0.67, so let's take it as 0.7. So the greatest electronegativity difference available of an S block hydride is actually 2.1 minus 0.7, that is 1.4. 1.4. So with that also, if you are to apply this theory, it looks like the bond is covalent. But the special thing with these S block hydrides are actually all of these S block hydrides I have marked. Other than the beryllium, all these block hydrides are considered as ionic. Even though the electronegativity difference is less than 1.5, still they are considered as ionic. Right? That is the most important thing to grab from here. All of these are considered as ionic hydrides. If one need to discuss the reasonings Why these guys prefer to form ionic hydrides? The thing is, actually, S block elements are very keen to release one or two electrons to come up with a noble gas configuration. So when it comes to group 1, it is with one more excess electron than the noble gas. If you are coming up with group 2 elements, those are with two more excess electrons than the nearest noble gas. So they tend to release those one or two electrons easily to come up with the noble gas configuration. They form ions. Group 1s form positive ions by releasing one electron. Group 2s form plus 2 ions by releasing 2 electrons when achieving their noble gas configurations. On the other hand, when it comes to hydrogen, hydrogen is very keen to accept an electron. Hydrogen is very keen to accept an electron. Why is that? Because then it can achieve the noble gas configuration of helium. As hydrogen is with one electron, then its nearest noble gas is coming up with the two electrons, the helium. So if hydrogen is to grab one electron, be in one electron from somewhere else, right? He can achieve the noble gas configuration of helium as H minus, There, it forms the H minus. So hydrogen is very keen to come up with this ionic form, right? H minus, as it can achieve the noble gas configuration, as well as this block guys. Those are very keen to achieve their ionic forms as they can achieve the noble gas configurations. So that even though the difference between the hydrogen and the S block atom in these hydrides are less than 1.5, both the hydrogen and S block atom are keen to come up as ions as they can achieve the noble gas configurations by doing so. So they will come up as ions and form ionic compounds. They will form the ionic compounds even though the electron difference is less than 1.7. So that is a very, very important point to grab from this reaction scheme. Right now? Okay. Let's write that thing as well. Right? Even though it is difference between, right, S element and hydrogen in these hydrides are less than 1.7, still these are considered as ionic hydrides, right? Reason? Reason? These are keen to form ions, as by doing so, they achieve noble gas configuration. Right? Okay, so just copy this stuff, right? Just copy this stuff. Right. Let's come up with the next decision. I think next decision is all about beryllium. But beryllium is supposed to do with the H2 gas. First thing is beryllium won't react under normal conditions with the H2 gas. Right? That is first thing to grab, right? This is a bit more about the beryllium stuff with the hydrogen gas, right? For our beryllium. Right? At normal conditions, beryllium won't react, right? At normal conditions, there are other S block elements react with H2 gas. Beryllium won't react. That is the first thing to note that. The second one, with extreme conditions, however, beryllium reacts with H2 gas to produce kind of a covalent hydride. This is very special, huh? Covalent hydride, right? Which will appear as a polymer. Which will appear as a polymer. Let's discuss this idea. So, Lama, if you are thinking of beryllium hydride, right? If you're thinking of beryllium hydride, so this is the beryllium hydride, right? BeH2, right? It's a covalent hydride. It's a covalent hydride. And see, it's electron deficient. You don't have the octet here as a group 2 as a second row element. So it's octet deficient. Octet deficient. One can say electron deficient. Some electron deficient hydride coming from beryllium. But this can be formed by reacting hydrogen in extreme conditions, not in normal conditions, right? Okay. Very high amount of heat as well as very high pressures are needed to produce this beryllium hydride, which is covalent and octet deficient, right? So that, right, as soon as it's produced, to overcome the octet deficiency, right, it will come up as a polymer like this. So these are the beryllium hydride molecules. Bunch of these molecules will connect with each other like this. So here you have 2 electrons, here you have with a bond 2 electrons. But this does is actually keeping 1 electron here, the other electron will be given to the space in between the other beryllium hydride and yourself, right? So that with that they will tend to form a new kind of a bond only with one single electron, like this. Half a sigma bond, half a sigma bond, half a sigma bond. Right? Even with this one, keeping one electron here, it will give the other electron to the space in between, so that it will form half of a sigma bond like that. So this is another way of trying to overcome the electron deficiency. With this one as well, the same thing occurs, right? Even with these, right? Even with these, right? So this can, right, provide one of the electrons to the space here, and can come like this. And even this one of the electrons can be given to this space like this, and can come up with this kind of a bond. Half of sigma bond, right? Is very important case, right? To grab that half of sigma bond, right? This goes like this, right? This will be also like that. So half of sigma bond coming from the next barium hydride, right? So that is the situation, right? So this is referred to as a polymer. Polymer, right? We can write it as BeH2 n times. BeH2 n times. It's a polymer. Normal n amount of these molecules will gather to come up with this polymer, right? Barium hydride polymer, right? Let's say BeH2 n times. Polymer form. Right? Here, I am discussing this thing, Lamai, because of here we'll come up with kind of a new idea. What is that? Before this molecule, before this thing, we had learned about half of phi bonds, half of phi bond. So we had discussed about some bond orders which are greater than 1 but lesser than 2, like that bond order equal to 1.5, the bond order equals to 1.33, the bond order equals to 1.66, kind of bond orders has been discussed. Anyway, up to now what we have discussed is always the bond order, right, was greater than 1. But this is the first instance we are learning where the bond order is less than 1. Bond order is in between 0 and 1. Here the bond order is 0.5, just 1 electron between the two atoms. So remember, bond order can take, right, any value from 0 to 3, from 0 to 3. It could be 0.5 as well, right? 0.5 as well. That is why I have discussed this molecule, right? Beryllium hydride. Okay. So with these kind of bonds are actually given a special name. Special name. What was the special name? The special name given to these things are actually in these cases you have two electrons, you have two electrons, right, going around three centers, three nuclei connected with two electrons, right? So those are referred to as, this kind of bonding is referred to as, right, three center two electron bonds. These are referred to as three center two electron bonds, right? Three center two electron bonds. Three center two electron bonds, right? Just draw this now. Just complete this. Right. This is what you need to know about the beryllium hydride, which is covalent and which will come up as a polymer. Right now? Okay. Let's move to the next session. Right? Let's move to the next session, which is at the page number 10 of your unit. So actually, with the discussion with the reactions of H2 gas, we had completed the discussion of S block elements reacting with right, elemental diatomic gases. In our available syllabus, we have to discuss such three instances where S block is reacting with O2 gas, N2 gas, as well as H2 gas. So that discussion is done with this discussion of H2 gas, right? Let's summarize the ideas what we have learned so far, right, with the reactions of elemental gases, right? Right. So this is at page number 10. As a special note, it is provided. This summarizes stuff, Lama. I'm not going to discuss much here, right? All the things we have learned. This is a summary as a special note, right? As the first point, it says, if they react, S-block metals produce oxides, nitrates, and hydrates with O2 gas, N2 gas, and H2 gas respectively, right? At that space, let's write this thing, right? All S-block elements, actually all S-block elements react with O2 gas, right? All S-block elements react with O2 gas, right? To produce respective oxides. Let's take this block element as M, react with O2 gas, right? To produce respective oxides. If it's a group 1, it is going to be like this. So if you are thinking of a group 2 element as M, oxide will come up in this form, right? Okay. This is a group 1 situation, and this is a group 2 situation. Right? So exchange of valence is a M plus O2 minus. M2 plus O2 minus. So 2 will cancel out. All will produce the oxides. Right? When it comes to reactions with nitrogen, reaction with nitrogen, not all the S block elements are capable of reacting with nitrogen. Only the S block elements which can come up with metal cations with high charge density can react with N2 gas. So that from group 1, only lithium will react with N2 gas to produce the nitride, and with group 2, all the guys will react, right, to produce those nitrides, right? So let's write that thing as well. So lithium and two A elements, two A metals. Let's take it as metals, this metal. All are metals, huh? So if you take the metal as M, react with into gas when heated to produce the respective nitrides, right? So nitride means N3 minus 4. I'll take it as N. If the group 1 is considered, the lithium is considered, N is equal to 1. If the group 2s are considered, N is equal to 2, right? Nitrates, right? So when it comes to hydrogen, reactions with hydrogen, other than beryllium, all the right S block metals will react with H2 gas when heated to produce the respective hydrates. And the special thing there is those are considered as ionic hydrates. Actually, all of these so produced guys are ionic compounds, right? Ionic hydrates, ionic nitrates, as well as ionic oxides, right? S block metals other than beryllium. Beryllium won't react with H2 gas under laboratory conditions, right? Extreme conditions are needed. So if you take the metal acid, react with, right, H2 gas to produce the hydrates. I put it as image in. If you are dealing with group 1, N will be 1. If you are dealing with group 2, N will be 2. Right? Special thing is these are ionic hydrates. All of these are ionic compounds, right? All of these are, right, ionic compounds. The oxides, nitrates, and hydrates are ionic compounds, right? Right? That is how these block elements are supposed to react with elemental diatomic gases. Right now, just complete this stuff now. Right. Let's discuss how these guys actually so form oxides, nitrates, and hydrates will react with water. Right. This is about that thing as well. How these so produce oxides, nitrates, and hydrates will react with water. Right. Okay. First, the oxides. Except beryllium and magnesium, right? All other S block S block oxides, right, will react with water to form the respective hydroxides, right? If you are to take some oxide as a group 1 oxide, I'll take the sodium oxide. As a group 2 oxide, I'll take the calcium oxide. If you're thinking of these guys' reactions with water, it's very easy to come up with the products. So as this one is kind of, these guys are kind of S block compounds. This block compounds reactions are ion exchange. S block compounds reactions are ion exchange, right? So that means you have the Na plus ion, O2 minus ion here. You have the H plus ion, OH minus ion here. So ion exchange NaOH, H2O, NaOH, H2O. But remember that we are not supposed to write the same chemical component at both sides of the reaction, right? So H2O is not written, right? So just the N unit is the product. So just think of calcium oxide reacting with water. So calcium oxide means Ca2 plus ion and the O2 minus ion. H2O can refer to as H plus ion and the OH minus ion. So if you are to connect the stuff, calcium hydroxide and H2O, calcium hydroxide and H2O won't be written. H2O won't be written, right? As we are not supposed to write the same component, same compound at the both side of an equation, right? That is how the so produce oxides of H block will react with water. Remember, the beryllium oxide and the magnesium oxide won't react with water. Right, we'll discuss that thing later. Right, with today's session later we will discuss how these oxides, as when we are discussing how these oxides and the metals will react with water. We'll discuss about this situation, why the beryllium and magnesium won't react, what kind of pattern they are appearing with the oxides react with water. We'll discuss the thing with the reactions with water, right? But keep that in mind. The beryllium and magnesium oxides, those produced when reacting with O2 gas, won't react with water, right? Other than that, other oxides of H block will react with water to produce the hydroxides, right? Now, let's discuss about what happens with the nitrides formed by these block polymers, right? So nitrides are normally formed by group 2s and lithium in the group with the group 1, right? Nitrides are formed only by, right, group 2 and lithium from this block, right? Those nitrides react with water like this. See, if you think of lithium nitride and the magnesium nitride, right? Just think what will be the products if they are react with water. You can easily predict, right? You can easily predict. So these are also S block compounds. If you think of S block compounds reactions, those are always ion exchange. So here you have the lithium plus ion and the N3 minus ion connects with the H plus ion and the OH minus ion. So what will happen? Lithium plus connects with the OH minus, that is lithium hydroxide, and H plus connects with the N3 minus, that is NH3 gas. NH3 gas. H plus with the N3 minus. Exchange of valence is H plus N3 minus. It is NH3 gas. So when the nitrides react with water, the hydroxide and the ammonia will be produced. Here as well, magnesium 2 plus, N3 minus are there, H plus and the OH minus are there. So magnesium hydroxide and NH3. Right? This ion exchange reactions. See, right? This is how nitrides produced by the lithium and the group 2 guys are supposed to react with water. They will produce the respective hydride as well as the ammonia gas. Just ion exchanges, right? Nothing much to remember, right? No need to memorize. Just what we need to do is just exchange the ions. The cation of this thing coming up with the anion of the other thing. Cation of this thing coming up with the anion of the other thing. So ion exchange will give you the product easy. I'm not going to balance the stuff, right? By looking at the both sides, you can just balance, right? Okay, this is how, right, the nitrides are supposed to react. Right now, let's discuss, right, how the hydrides produced when the S block is reacting with H2 will react. with water, right? Okay, these are done, right? Let's discuss how the hydrates will react. So except beryllium, all the other S-block elements form hydrates with laboratory conditions, right? All other S-block hydrates will react with water through ion exchange reactions, right? Let's take the right sodium to represent the group 1 and magnesium to represent the group 2. Sodium hydride will react with H2O. Even the magnesium hydride will react with H2O. What kind of reaction, what kind of products we expect? In sodium react with H2O, it is a kind of ion exchange, right? It's block compounds. When it's block compounds react with others, right? With water even, as well as acids, right? Ion exchanges occur, right? H plus, Na plus and H minus, the two ions. Here you have H plus and the OH minus. Exchange the ions, right? Na plus coming up with the OH minus here, so that is NaOH. H plus coming up with H minus. H plus and H minus, that will give you H2 gas. H2 gas. Here as well, magnesium 2 plus and H minus ions are there. Here you have H plus and OH minus ions. So magnesium 2 plus coming up with OH minus, that is magnesium hydroxide, and this is H plus and H minus H2. Right now, so when S-block hydrates are react with H2O, will have with respective hydroxides as well as H2 gas. Right now, gas liberations, right? Okay, just write this thing as well. All of these are considered as ion exchanges. Ion exchanges, right? So another space provided there, and the page number 10, we'll discuss a bit more. Now, when it comes to S-block metals reactions with O2 gas, we had seen some elements are capable of producing not only the oxides but also peroxides, and some were able to produce superoxides as well, right? Let's discuss how these peroxides and superoxides are supposed to react with water, right? Those are also kind of products coming up with reactions with elemental diatomic gases, the peroxide and superoxides. You remember who are the guys which are able to form the peroxides? So sodium is able to produce a peroxide, and potassium, rubidium, cesium, as well as from the group 2, the beryllium, Ba, the bottom element, the most reactive one, and the group 2, barium, is also capable of producing peroxides. When it comes to peroxides, the potassium, rubidium, and cesium, the bottom 3 of group 1, which are the highly reactives, right, of the group 1s, are able to produce superoxides, right? So those peroxides and superoxides as well will react with water to produce some compounds, right? Well, let's discuss what will be there, right? Right. So peroxides. Peroxides with water. Peroxides with water. Water. Right? How these guys are supposed to react. Right? So let's come up with sodium. sodium peroxide with water. Right? Again, S block compound with water. So ion exchange. So here you have the Na plus ion, two of Na plus ions, and O2 2 minus, O2 2 minus ion, the peroxide ion. Here you have the H plus ion and the OH minus ion. Right? Let's do the ion exchange. Come up with products. Na plus connected to the OH minus. It's going to be NaOH, and O2 2 minus connected to the H plus. It's going to be like H plus and O2 2 minus. H plus and O2, that is, if you have to exchange the valencies, one comes here, two comes here, that is H2O2. See, H2O, H2O, you produce the H2O2, right? So if you are react a peroxide with water, yeah, what you will obtain is H2O2. Very clear, right? H2O2 ion exchange reactions. So what about the superoxides? Superoxides, right? The O2 minus 4. So normally superoxides are produced by potassium, rubidium, and cesium. Right? This is us. What happens when you want to add water to potassium superoxide? Right? KO2 solid with water. Right? The idea is this, Lamai. Right? We could think of superoxides O2 minus, actually two particles of superoxides as a combination of a peroxide and O2 gas. The combination of peroxide and O2 gas. We can view the superoxide like this, right? 2 of O2 minus superoxide is equal to peroxide plus O2 gas. Peroxide plus O2 gas, right? So this is mass conserved as well as charge conserved. You have 4 oxygen atoms here, 4 oxygen atoms. The charge minus 2, minus 2. So apply this thing. Apply this thing to here. So to apply this thing, first you need 2 of superoxides. So put some 2 here. So now with this you have 2 of K pluses. Instead of 2 of peroxides, I write 2, instead of 2 of superoxides, instead of 2 of superoxides, I write peroxide plus O2, peroxide plus O2, right? This will react with H plus and OH minus coming from this 2. So now again do the ion exchange, that will give you the products. So you have K plus sign, and then ion here is OH minus, that will give you KOH. It will balance right there, right? You may need 2 here. 2 of OH minus are needed. And H pluses will connect with the anion here, right? Giving you the H2O2, hydrogen peroxide, and O2 will release as well. O2 will release as well. Right? That is how we are supposed to balance that stuff. Right? So here as well, some 2 is needed here, and some 2 here. Right? 2 of these things are needed to produce H2O2. 2 of which plus are needed to connect with the 2 minus charge. So 2 of OH minus is provided by the air, and 2 of Na pluses are there. So altogether 2 of NaOH and H2O2. Right? This is how they are supposed to react with water. Right? Just write these 2 things as well. right නේ ටික ගන්න right. Let's discuss about the reactions with compounds. So what we have completed is actually the reactions with right diatomic elemental gases. Right, let's move towards the reactions with compounds. Let's look elements, reactions with compounds. Right. Okay. So reactions with compounds. Right here, we are supposed to discuss about how these S-block metals will react with acids, and then how they will react with water, or one can say H2O, that compound, and how those things will react with ammonia. Right, that is our major discussion here. Right, actually acids like HCl, H2SO4, so water, NH3. Actually, most of them can be considered as hydrates. H2O is the group 16 hydrate. NH3 is kind of a group 15 hydrate. Right? If you are referred to the the HCl, that acid is kind of a group 17 hydrate. So basically, this can be referred to as how these S-block guys react with group 15, 16, and 17 hydrates. Okay, let's start our discussion with how these guys react with acids. Let's concern on the lead acids first. Right? Reactions with acids. Reactions with acids. First, the hydrogen acids. Right? With the hydrogen acids. Right? Okay. How these gases react with the hydrogen acids. Right? So, it is very normal. Right? So, if you have to consider, let's consider with deal H2SO, will deal with HCl first. The thing is very simple now. Right? If you have to refer the reactions with group 1A, right? Let's copy stuff, right? If sodium is to react with, so let's take it as M, better, let's take it as M, representing all the metals at group 1. If M is to react with HCl, so again we observe is a reaction of S-block element. It's a reaction of S-block element. But if you are considering reactions of S-block elements, those are all about redox reactions. Redox reactions. The S-block element oxidizes and forms the cation and combines with the anion. coming from the other species. That is how S-block elements are to react, right? S-block element oxidizes and forms a cation and connects with the anion coming from the other reactant. And other reactant should have something to reduce as well. So here the M will oxidize and connect with the anion, the Cl minus Cl, and the H plus here will reduce to H2. That's how the salt and H2 is produced when these S-block metals are to react with acids, right? So M reacts with HCl, right, to produce the salt and H2 gas. So if you are thinking of group 2s, right, it's the same kind of reaction would occur with HCl, right? This guy oxidizes to M2 plus and connects to the anion here, Cl minus, right? M2 plus Cl minus, that is MCl2, and this H plus reduces to H2, right? This is how we are supposed to come up with the reaction. So balancing is very easy, right? Not that much hard, right? You can have some 2 here to balance the stuff, right? In this case, right, again you need some 2 here as H2 is produced, so you need some 2 here and here as well, right? With dil H2SO4 also you would observe kind of salt and H2 is producing, right? The same stuff, right? So document oxidizes and connects with the anion from the acid. In this case, it is SO4 minus, and the H plus of the acid will reduce to H2. That is the idea. Right? Simple as that. So if you are to take the M as group 1 element reacting with H2SO4 diluted, what happens? This guy oxidizes as M plus and connects to the anion here, SO4 minus. So M plus and SO4 minus. So SO4 minus, it comes here. Salt and H2, the hydrogen of the acid, will reduce to H2, right? So balancing needed some 2 here. So if you are coming up with magnesium kind of group 2 element with H2SO4, the same logic can be applied. M2 plus coming from oxidizing the M will connect with the SO4 minus ion here. So that is MSO4 as the salt, and H plus from here will get reduced to H2. Salt and H2 will be products when S-block metals react with dil acids. Right? The thing is clear? The thing is clear. Right? Salt and H2 will be product when S-block metals start to react with dil acids. Right. Let's discuss a bit more about these reactions. Some more you should know about these reactions. Now, in small ages, right? In small ages, basically in O levels, right? In O levels, you had learned that when an acid is react with a metal, when an acid is to react with a metal, you have learned that the salt and H2 will be products. Salt and H2 will be products. In O levels, you have learned that. But remember That is not true for each and every metal. That is not true for each and every metal. That is true only if the metal you are concerning is above hydrogen in the activity series. The metal you are concerning is only above the hydrogen in the activity series only. That statement is true. Right? Okay? This is just a bit more about that thing. Right? Fortunately, all of the S block elements, right, come above hydrogen in the activity series. So that for all the S block elements, that statement is true. S block elements react with acids, deal acids to form the salt and H2. That is true. As S block elements are coming above hydrogen in the activity series. But not all the metals are capable of forming the salt and H2 with the deal acids. This is just about that point. Right? The idea is this. So if you are referring to activity series, right? So I need some space here, right? Right? If you are referring to kind of activity series, right? Right? This is just the theory behind these reactions, right? I'll come with the activity series first of all. You have the potassium. Let's come with some elements in the activity series. Sodium, calcium, magnesium. These are the S block guys. Then you have hydrogen, and then you have the copper and the rest, ending up with gold. Gold, AU, over. Right? So these are the block guys. So you clearly see these block guys are above hydrogen in the activity series. So if you are thinking of a reaction between two species in your activity series, if you are thinking of a reaction between two species in your activity series, how they are supposed to react? This is just about that thing. How they are supposed to react. So in your small ages, you may have come across these reactions, right? The zinc reacting with copper sulfate. What will happen? The zinc oxidizes and form the zinc 2 plus and connects with the anion here. Zinc sulfate, and copper reduces. Copper 2 plus reduces. This is what happens. So here what you have is the Cu2 plus ion and the SO4 minus ion. So what happens here is zinc oxidizes and connects with the anion here to come up with the zinc sulfate like this now. And copper 2 plus reduces to copper. Right? This reaction has been learned in your small ages. If you are supposed to react the copper with zinc sulfate, actually no reaction would occur. You may have learned about these things in your O levels. Why is that? What was the reason for that? The reason is actually, if you are considering a reaction between two guys in your activity series, the most active guy, which is at the top, relatively top, should get oxidized, while the other should get reduced, right? So that is why this happens like this. So zinc is actually above hydrogen in the activity series. So that zinc is above copper in the activity series. So in a reaction participating copper and zinc, definitely copper should be the one to get oxidized, and zinc should be the one to get oxidized, and copper is the one to get reduced, right? As zinc appearing here, right? As zinc is above copper in the activity series, right? If you are thinking of a reaction between the copper and zinc, right? Basically, zinc, which is above, right, directly above, should get oxidized, while the copper, which is directly below, should get reduced. That is how a reaction would occur among two species at the active series. Right? That is what happens here. Zinc get oxidized, zinc converted to zinc 2 plus, it's kind of oxidation, and copper 2 plus coming up as copper, it's kind of a reduction, right? Okay, so remember that if you are considering reactions in an active series, right, the top guy should get oxidized, right, and the bottom guy should get reduced. Bottom guy should get reduced, right? This is how a reaction will occur among two species in the active series, right? According to this, right, if you are reacting with hydrogen and a metal, when we are thinking of reactions involving hydrogen and metals above the hydrogen in the active series, they are the metals above the hydrogen will get oxidized and hydrogen will get reduced. Hydrogen will get reduced. That is what we see here. Metals above hydrogen, as this block is appearing above hydrogen, those will get oxidized to M plus form or M2 plus form, while hydrogen H plus get reduced to H2. It's reduced to H2, right? So in these reactions, S block metals get oxidized to form the salt, right? While hydrogen, the H plus from the acid get reduced to H2. H plus from the acid get reduced to form H2 gas, right? That is what happens, right? Now, this all happens according to activities. So if you are thinking of a metal below hydrogen is activities, if you are thinking of a metal below hydrogen is activities, that can't be happen because they are then the hydrogen is the one to get oxidized. The below metal should get reduced. So hydrogen with the H plus form in your acids can't get oxidized further. So the highest oxygen state available with the hydrogen is the plus one. So it can't get further oxidized, right? So that as in acids, hydrogen is available as H plus. So it can't get further oxidized. So that reaction won't occur if a dilyl acid is added to a metal below hydrogen in the active series. Right now, that is the idea. So if you are to think of a reaction among two species in your active series, basically the most active guy, which is above, relatively above in the active series, should get oxidized, while the least active guy should get reduced, which is relatively below in the active series, right? Okay, that is the idea. So this is the theory behind this reaction scheme, right? So you can write this stuff as well. This is how the active series knowledge is related to these reactions, right now. Okay, just complete this stuff. Right now, okay, this is how the S block guys will react with the lasses, right? Let's discuss how these guys are supposed to react with concentrated acids, right? Okay. Right. Reactions with, let's say, concentrated acids. Right, when it comes to the reactions with conc acid lamine, right, not like in dill acid situation, here the reduction will occur not from the hydrogen, right? When it comes to the dill acid reactions with S block metals, what we have seen is S block metal oxidizes. While that happens, the H plus from the acid get reduced now. But when it comes to the reactions with conc acids, right, not the H plus from the acid, but the P block element appearing with the acid. When it comes to H2SO4, the sulfur. When it comes to HNO3, the nitrogen. That will get reduced there. Let's discuss why is that and how to write the reactions. Right? So the case is this. Lamine, if you are considering dill acids, right? If you are considering dill acids, right? So with dill acids, the H plus ions, if you are considering H2, HCl, the H plus ions and Cl minus are as two separate particles, completely dissociated. The bond between the H and the C, H plus and the Cl, H and the Cl is completely dissociated to give the H plus and the Cl minus. When it comes to H2SO4, those will be completely dissociated. My HSO minus O, one can say H2SO4. So, right, one can say H plus and SO4 2 minus. Right, so that when your metal releases, when your metal releases those electrons, those will be actually accepted by the H plus ions. So negative ions are not going to accept negative charge electrons. Those will be attracted by the H plus ions to reduce to H2. This is what happens with the dill acids, right? But when it comes to conc acids, that is not going to be the case, right? That is not going to be the case. With conc acids, most of the acid molecules are undissociated. Undissociated like this. Right? Conc situation. Right? So that the electrons released by the metal is not going to accept by the hydrogens but by the p block metals. Why is that? The hydrogen is carrying 2.1 electron, sulfur is carrying 2.6 here. So sulfur is more keen of electrons than the hydrogen. So the electrons released by the M will be accepted by the sulfur here, not the hydrogen. In this case as well, hydrogen is coming up with 2.1 electron, nitrogen is coming up with 3.0 electron. So nitrogen is the one to accept the electrons to get reduced, not the hydrogen. So that with conc acids, while S block metal oxidizes and coming up with the salt, the sulfur and the nitrogen of conc nitric and the conc sulfuric, right, will get reduced, not the H plus from there. As Lama, these guys are not completely dissociated, right, with conc acids, right, not completely. dissociated. Here also not completely dissociated, right? Actually, these OH bonds of sulfuric as well as nitric are covalent, are covalent. So you don't have enough water molecules to polarize the covalent bond there to break and release the H pluses when it comes to conc acids, right? So in this with the dill acids, right, you have more water molecules. Dill acids means more water molecules are there, diluted. More water molecules are there, so that they can polarize the OH bonds, and break them to come up as ions to release the H pluses. Here, the HCl is normally a covalent molecule, right? So, in the presence of high amount of water, the water molecules will polarize the OH, polarize the HCl bond and break that to ions. That is how the H pluses are released when the diluted situation is there, when the dill acids are used. But with the conc acids, you have not enough sufficient amount of water molecules to polarize those OH bonds to provide the H pluses to the medium, right? So that most of the conc acid molecules are appearing as undissociated, so that the electrons release will be grabbed not by the hydrogens but by the sulfur and nitrogens in conc nitric and conc sulfuric, right? That is what happens here. That is the picturized idea with the reactions of conc acids. So let's come up with the reactions then. So with, if you are regarding with conc H2SO4, very a little amount of water is there. So the reaction would look like, right, let's come up with magnesium. Magnesium will react with conc H2SO4, right, to produce what? The magnesium oxidizes to Mg2 plus and connects with the anion here. That is magnesium sulfate. And sulfur from H2SO4 get reduced to SO2 gas, right? It's very important to note that the sulfur is the one to get reduced here, not the hydrogen. And to balance the reactions, redox reactions, normally you need some water. If your oxidizing agent or reducing agent contains, right, contains kind of oxygen there, to balance the redox reaction, you may need water, right? So what about the reactions with conc nitric? Let's consider it with magnesium. Normally highly active metals are not going to react with these considered acids, right? Some vigorous reactions, extreme reactions will occur, right? Magnesium oxidizes and connects with the anion to form the salt, magnesium nitrate here. And here as well, nitrogen is the one to get reduced, not the hydrogen. So plus 5 oxygen state of nitrogen here will get reduced, right, to NO2 gas, and both will be produced, right? So that is the reaction. Consider reactions. So balancing these things are not that much hard, Lamai. Right? No need of memorizing the stoichiometric values, right? Balancing these are not hard, right? So if you need, I'll balance one. Right? I'll balance this magnesium with H2SO4. So balancing will be done like this, right? So we have the magnesium. So we have the H2SO4, right? Magnesium oxidized to Mg2 plus. H2SO4 oxidizes to SO2, right? This balances stuff. So magnesium 0, Mg2 plus 2 electrons. So 2 electron difference. sulfur here plus 6, this plus 4, again 2 electron difference, electrons are balanced. Then charge balancing, you have 2 plus charge at this side no charge, so to balance that thing 2 of H pluses are needed. To balance the hydrogens, you have 2 hydrogens, 2 here, altogether 4 hydrogens, so that 2 of H2O are needed, right? So H pluses are provided by H2SO4 molecules, so this will give you can add some SO4 2 minus here, so to write this as H2SO4. So one SO4 2 minus is added to the left hand side, that should be added to the right hand side as well, that will be given to this, so MgSO4. So thing is balanced, so we'll come up with this H2SO4 and this H2SO4 altogether 2 of H2SO4 with 1 magnesium, giving you magnesium sulfate SO2 and 2 of H2, right? 2 of H2O. Right? Balancing is not that much hard. Let's come up with the balancing of this one as well. Let's think of balancing of this thing as well. Right? Don't try to remember, right, the stoichiometry values, right? No need, right? You should be quickly able to balance this stuff with the use of reduction method, right? Even by inflation, you can balance the stuff, right? Let's balance the magnesium with HNO3. So magnesium will oxidize to Mg2 plus. HNO3 will reduce to NO2, right? Let's balance the stuff. Magnesium 0 oxygen state plus 2 oxygen state. So 2 electron difference, right? Nitrogen with plus 5 oxygen state here, plus 4 here, 1 electron difference. So to balance the electrons, oxygen states, right, you need some 2 here, so 2 coming up here as well as here. So now balancing the charges, you have 2 plus charge here, nothing here, so that you need 2 of H pluses to balance the charges, and to balance the hydrogens, you have 2 here and 2 here, 4 hydrogens, that means 2 of H2O are needed, right? Okay, so these H pluses are provided by the HNO3 acid, so we can write here as 2 of HNO3. For that, you had used 2 NO3 minus ions by hand, so that can be added to here. So this is going to be Mg nitrate twice, right now. So that is balanced, right? So 2 of HNO3 plus these 2, altogether 4 of HNO3 will react with the 1 magnesium and will produce magnesium nitrate, 2 of NO2 and 2 of water. Right now, it is how we are supposed to balance the stuff, right? Balancing is not that much hard there, right? Okay, just complete the stuff now. Right. Okay. Let's come up with the next reaction scheme. So what we have just discussed was actually the reactions with acids. Right. Let's move towards the S block elements reactions with water. Right. Right. Reaction with H2O, right? Reaction with H2O. Reaction with H2O. This is us, right? It's like this, Lama. So if you are to consider this block, If you consider this block like this, lithium, sodium, potassium, rubidium, cesium, beryllium, magnesium, calcium, strontium, barium. If you consider this block here like this, going down as atomic size increases, ability to get oxidized will increase, right? So that reactivity will increase, right? Going down, the reactivity will increase. So we can say ability to oxidize will increase, so that we say reactivity increase going down, right? And the other thing we know is going towards this side, reactivity decreases, no? So as atoms become smaller, ability to get oxidized, so releasing electrons becomes hard, right? Decreases, so that we say reactivity decreases, right? So that lamine, the smallest, right? The smallest reactivity or the least reactivity out of S block elements is with beryllium, right? Going towards right hand side, reactivity decreases, as well as going towards up, reactivity decreases, right? Going down, reactivity increases, means going up, reactivity decreases. So that least reactivity is with beryllium. So beryllium is the hardest one to react in this block. The next hardest is the magnesium. Next hardest is the magnesium. Those are the two metals with the least reactivity in S block when concerning the reactivity with water as well, right? Okay, so reactivity trend can be taken or can be classified into three sections: with water, with H2O, right? So these guys with greater reactivity will react with all forms of water, will react with all forms of H2O, react with all forms of H2O, right? It will react with cold H2O, or one can say cold water, and with hot water, and react with steam as well. All considering forms of H2O, the highly reactive elements will react, right? Let's discuss about these wordings, what this cold water means, what this hot water means, and what this steam means. Lamine, right? This cold water means actually, right? H2O between temperatures 0 to room temperature, let's say 30 Celsius. This is what cold water means. Hot water, what this hot water means? Hot water means actually that is H2O liquid. Water means H2O liquid. Water means H2O liquid. H2O liquid, which is some temperatures greater than 30, and less than 100. After the 100, the liquid state won't appear with H2O. The steam means, steam in this sense means it is H2O beyond 100. So it is H2O gas, right? So temperature is beyond 100. So normally 450 to 500 Celsius. That is the available temperature with the maximum temperature with the laboratory techniques, right? Laboratory equipments. Right? So the most reactive guys will react with all forms of water. Sorry, all forms of H2O. Sorry, all forms of H2O. Water means just the H2O liquid state, right? With the all forms of H2O, the more reactive guys will react. But to start reactivity with magnesium, you need some energized water. You need some energized water. With cold water, no reaction with magnesium, so its reactivity is less than these guys. But it start its reactivity with H2O with the hot water, right? So with hot water, magnesium starts its reactivity. So that is with steam as well, it will react. If you are reacting with hot water, that conditions, definitely it will react with more vigorous conditions. When it comes to beryllium, it is the least reactive guy in this block. It needs some extreme conditions, greatest conditions, more energy to react, as it is the least reactive. So beryllium won't react with the liquid water, won't react with the liquid H2O, that means won't react with water. To start its reactivity, beryllium needs H2O's gaseous form, highly ionized form. So only with steam, beryllium won't react with water, won't react with water. Water means the H2O liquid state. That energy is not enough with water to react with beryllium. Right now? Okay. So that is the summary of reactivity of S block elements with water, right? So quickly complete this stuff. Right. Let's copy the reactions here. Let's copy the reactions here. Right. Okay. Let's copy the corresponding reactions. Right. First thing, first let's discuss about the reactivity of these guys. Reactivity of these guys. These will react with all forms of H2O. Right. It says except, right, beryllium and magnesium, all other elements react with all forms of H2O, hot water, hot water, cold water as well as steam, and liberate H2 gas. See how the reaction occurs. So let's consider M as the element representing all of these guys. So M solid will react with H2O, right? It could be cold water, hot water or steam, or even the steam, with all forms of water, H2O. It will react, right, to form what? What will happen? This guy oxidizes and connects with the anion of this thing, right? MOH hydroxide. I put it as in. So if it is a group 1, MOH only, but if it is a group 2 like calcium, strontium, barium, it will be MOH2, right? And H2 will produce, right? Here M represents, right, all less block elements other than beryllium and magnesium, right? Okay, got the idea? All right. So you need some examples. So let's come up with reaction with lithium as well as lithium reaction with calcium, right? So lithium will react with H2O. It could be cold, hot, or steam to produce the lithium oxidizes and connects to the anion here. Come up with the lithium hydroxide plus H plus from here will get reduced to H2. So calcium with H2O, it could be cold, hot, or steam. Calcium oxidizes and connects to the anion here. So calcium hydroxide and H plus reduces to H2. So balancing is not that much hard, right? So 4 hydrogens are there, so 2 is needed here. There is balance, right, for this one. So 1, so maybe needed 2 here to come up like this. Right? This is how these guys will react with H2O, with all forms of H2O discussing in the A-level syllabus, right? These more reactive guys will react, right? Okay, let's discuss about the magnesium scenario. Reactions of magnesium with H2O. I erase this stuff, right? So when it comes to magnesium lamine, magnesium won't react with cold water. Magnesium won't react with cold water. Won't react with cold water. And it starts its reactivity with hot water. With hot water. With hot water slowly reacts, right? Slowly reacts. Very slowly, right? With hot water, very slowly reacts. And will produce, right? This one can take it as H plus and OH minus. So magnesium oxidation can with the OH minus here, that is magnesium hydroxide, plus the H plus from here get reduced to H2, right? So that is how the things occur, right? Balancing is that much hard, right? So what about the magnesium reactivity with steam? The H2O's vapor state, the steam, right? When it comes to steam, the H2O's gaseous state, right? They are the surproduced magnesium hydroxide will decompose when you apply more and more heat beyond 100, right? When the heat approaches kind of 500, but magnesium's hydroxide will decompose to magnesium oxide and H2O. So we are not supposed to write the H2O at the both sides as H2O as a reactant as well. So it will produce the magnesium oxide and H2 will also produce. So by examining this thing, we can see the H plus here has been broken to H2O here has been broken to H plus and O2 minus. So there magnesium get oxidized and connected with the O2 minus anion coming from the H2O, and H plus from here get reduced to H2. That is how the reaction would occur with magnesium when it is react with steam, the H2O's gaseous form. Right now? Clear? Right. Let's write the reactions with beryllium acid. Right? Let's write the reactions with beryllium acid. Right? I'll write it here. Reactions of beryllium with H2O. The thing is, Lamai, beryllium won't react with water. That means beryllium won't react with H2O's liquid state. Beryllium won't react with H2O's liquid state. So that we can say beryllium won't react with water. It starts its reactivity with the H2O's gaseous form or the vapor phase. Right? So with steam, the beryllium reacts but not with water. Right? So if there's a statement like beryllium reacts with H2O, that is true. Beryllium reacts with H2O, that is true. But if they have said beryllium reacts with water, that is false. That is false. Water is not just the H2O. Water is the H2O's liquid form. H2O's liquid form. So beryllium won't react with H2O's liquid form. Right? But beryllium reacts with water when it is at the gaseous form, or one can say when it is as a steam. Right? Okay. Beryllium reacts with H2O but not with water. Right? Okay, reactions of beryllium with H2O, right? So let's write beryllium. If you think of it in H2O liquid, cold water could be the hot water. cold water, hot water. The thing is, beryllium won't react with water. No reaction. No reaction. To start reactivity with this beryllium, which is the least reactive out of this block, guys, right? We need steam. The energized H2O, highly energized H2O. Steam is needed. So it is not the liquid state, it is the H2O's gaseous state or vapor state. So here, as steam is used, right, with the metal with high charge dense cations, right? We are expecting for H2O to break as H plus and O2 minus. So basically, high charge dense cations will prefer high charge dense anions. High charge dense cations will prefer high charge dense anions when coming up with the products. Right? So beryllium prefers the oxide form. So low charge dense cations, metals with low charge dense cations prefer, right? Metals with low charge dense cations prefer anions with low charge density, right? But metals with high charge dense cations prefer high charge dense anions, right? That is how the beryllium will participate with reactions with H2O, right? This completes the stuff with beryllium as well, right? These are reactions with, right, this section, and these are the reactions with magnesium, and this is the reaction scheme with beryllium, right? Okay, let's complete the stuff now. Right, man. Okay. Right. Let's discuss a bit more about the reactivity with water for some other elements as well. Right? What we have discussed so far is actually how these S block metals will react with H2O. Right? So we'll discuss a bit more. What about the other metals in the activity series? How they behave with H2O, right? This or that thing as well. So when they ask questions in the A levels, they are not only concerning on this block, no. If you are thinking of a right MCQ, they are not only concerning on this block, no. Right? From all the metals in the activity series, they will ask questions. So let's discuss how the other metals of the active series will react with H2O. Right? So for this thing, we have to consider electrochemical series. We have to consider the electrochemical series. Right? This is all about the reactivity with water. Right? Activity series and reactivity with H2O. Right? Even though it is referred to as activity series, we'll discuss about the electrochemical series. What is this new term, electrochemical series? Right? Electrochemical series is almost the same as the activity series, but with the electrochemical series, what we are referring to is actually the reactivity with water element. So activity series is kind of a general series which will discuss reactivity with all the stuff, right? Even for thermal decompositions, right? Reactivity with uh, all the reactions generally is considered by the activity series. But electrochemical series is kind of a thing which is most of the times, right? The reactivity is concerning with the aqueous medium, right? So when it that is almost the activity series, right? But few changes are there. The most important change there is the lithium is actually at the start of the electrochemical series because it has a kind of a reactive guy, right? With water, right? Okay, so lithium, potassium, calcium, right? Magnesium, aluminium. So activities, right? One can say this is activities, right? Okay, no worries, right? Okay, when it comes to reactivity, right? Up to here, up to magnesium, the things will react with the reaction starts with cold water. Reaction starts with cold water. Reaction starts with cold water. With cold water, reaction occurs. Right? Okay. From the magnesium, actually magnesium, its reactivity starts with hot water. Hot water is needed to start reacting magnesium with H2O. Right? Till tin, till tin, the elements will react with H2O. But for these things, they need steam to react with. But beyond tin and beyond that, right? No reaction, no reaction, no reaction with H2O, with any kind of H2O. Right? That is what we know. Right? That is what you should know, right? So with this diagram, I'll discuss about the oxides as well. I'll discuss about the oxides as well, the metal oxides. Right? I'll discuss about the metal oxides as well. Right? From this section, right, until the magnesium. to this side, active side, right? Oxides. Metal oxides will react with water. Metal oxides will react with water. React with water, H2O, at water at room temperature. To produce metal hydroxide. To produce metal hydroxide, right? To produce metal hydroxide, right? Beyond this, beyond magnesium, and after that, if you're considering metal oxides, those won't react with H2O at room conditions, right? At room conditions. Right? These oxides will appear as precipitates. Right? These oxides and hydroxides will appear as precipitates. Right now, that is how they react with water at the room conditions. Right now, so just complete this diagram as well. Right, at the space given there at the page number 12 of it. This will be important, Naman, when answering questions. This will be also important, right? Right. let's come up with the next reaction scheme. So today we had done how these guys react with acids. Now we had completed how these guys react with water, and then we'll discuss how these H2O guys are supposed to react with ammonia, the industry gas, right? Right. Now let's move towards the reactions with ammonia, right? Reactions with NH3, one can say ammonia, right? Let's discuss how these guys will react with ammonia, right? Okay, right? Let's consider there are two categories. We can divide the S block into two categories when concerning the reactivity with ammonia gas, right? So the two categories are coming up as metals which contain cations with low polarizing power, and the next category contains metals with cations with high polarizing power. Right? We can divide our into two sections, right? So lithium, beryllium, magnesium, calcium, strontium, and barium. Coming up as metals with cations with high polarizing power, right? Or high charge density. So for these, charge density is high, yeah? Q plus O R plus is high, right? And the next section, sodium, potassium, rubidium, and cesium. Those are with, these are the metals with cations with low charge density, right? So we can say charge density is low, Q plus O R plus is low, right? Let's see how these guys will react with NH3 gas, right? So if you are referring to the guys with high charge density, the guys with high charge density, like this, right? Like this. If your cation is with high charge density, then your cation is able to attract electrons from all the three NH bonds, like this, as your cation is with high charge density, right? And those bonds will polarize heavily, so that three hydrogens will be released as H pluses, and you will form the N3 minus anion. You will form the N3 minus anion, as all electrons from all the three bonds will attract towards 90, ultimately to form the N3 minus. All these three electrons come towards 90 and form the N3 minus. And H pluses will be released, and by the electrons released by the metal to form the cation, right? Those H pluses will reduce to H2, right? So that as charge density or the polarizing power of these things are high, this section, right, it will produce the metal nitride and H2 gas as products, right? Metal nitride and H2 gas as products. In 3 minus plus H2 gas will be produced as products, right? Right, one can say attract electrons from all three NH bonds, to make or to form N3 minus nitride, right? That is what the cations with high Bohr's power or high charge density do. But when it comes to the situation with cations with low Bohr's power, with the low charge and greater radius, those guys are not able to attract electrons from all the three bonds because their Bohr's power is smaller, or charge density is smaller, in power is smaller, so that those will attract only one pair from these three NH bonds, right? So that only one electron from these hydrogens will come towards nitrogen and form the NH2 minus, and H plus will release as that happens, right? That H plus will grab the electrons released from the metal when forming the metal cation produced as H2, right? So we can say attract electrons from only one NH bond to form NH2 minus amide, right? So cations with low charge density forms NH2 minus salts by releasing H2 gas, right? This is the idea, right? So these guys will form the amides, NH2 minus salts with H2 gas when reacting with ammonia, and these guys will form the nitrides with the releasement of H2 gas when reacting with ammonia, right? The things are clear, right? Quickly, right? Just complete this stuff. right? Okay, let's write the reactions now. Let's write these reactions, right? For group A as well as group, for these guys as well as these guys, right? I'll erase this, right? For 1A, right? Because 1A, group 1A, right? Lithium form the nitride, lithium form the nitride, right? As we can think of this one as H plus and N3 minus, the two ions. The high charge dense anion is preferred by the high charge dense cation. The lithium is the one with the greatest charge density among the group 1 elements. So this one will oxidize to Li plus and connects to the anion here. So Li3n, N3 minus, no? And H plus here will reduce to H2, right? So other metals, in group 1, that means sodium, potassium, rubidium, and cesium. Right? Let's take M as the general form. Those will react with NH3 gas needed to heat, right? They are, as those are with low charge density, the other metals of the group 1, right? Those will prefer the anion with the low charge density NH2 minus. So this oxidizer sign connects to the anion here. So as those are group 1s, right? M plus connects with the anion NH2 minus. So M NH2 plus, the H plus will reduce to H2 gas, right? This is how the group 1s will react with ammonia gas, right? Not hard to balance the stuff. 4 are there, so we need 2 here, right? It's balanced, right? Okay, right? This is not hard to balance again, right? 3 things are there, so 2 here, so to balance the 3, right? And here the 3 is there, so this completes on 3 here. So balance the 3 things like this, right? 6 things are there. So some 2 is needed with 6 and some 3, right? Okay, what about the group 2As, right? All the group 2As are considered as containing cations with high charge density, group 2As, right? So all of them will produce nitrides. The cations with high charge density, cations with high charge density prefers the anion with the high charge density, N3 minus, right? Okay, so we can see all, right, 2A metals, all 2A metals. Beryllium, magnesium, calcium, strontium, barium, right? All 2A metals, right? We can consider M as the general form of the 2A metal. Will react with NH3 gas. So we can break this one as H plus and N3 minus. So we are dealing with kind of cations with high charge density, right? So cations with high charge density prefers the anions with high charge density, right? So M will oxidize to M2 plus as it's a group 2 and connect the anion here. So M2 plus and N3 minus. So N3 minus comes here, M2 plus comes here. It is a salt, and H plus will reduce to H2, right? So balancing 3 here, 2 nitrogens, so all to the hydrogens, 6 hydrogens, so some 3 is needed here, right now. Okay, it is done. So these are reactions, right? Okay, always keep that in mind. The cations with high charge density, these guys, or high porous power, prefers the anions with high charge density, the N3 minus, the greater charge with one atomic space or radius. QOR is the charge density. So cations with smaller charge density prefers the anion with smaller charge density, right? Just -1 charge, low Q value, and R value is high because with 3 atomic space. Right now, okay, that is how they are supposed to react with NH3. Clear? Just, the next thing to grab from here is actually we need to discuss what will happen if these so produced products, the amides and the nitrates, are supposed to react with water. We have discussed that thing again and again, right? Even with the reactions with the O2 gas, even with reactions with N2 gas, hydrogen gas, right? The so produced products, how they supposed to react with water has been discussed. So let's react with this as well. How these guys are supposed to react with water, right? So let's come up with that thing as well. This is special thing. This is special thing when it comes to these guys' reactions with water. Now see, this S block metal will react with ammonia to form a salt. The special thing happens here is if you are to react this salt with water, right, that will again produce the NH3 gas. That is the special thing here, right? So this thing coming up with lithium plus and N3 minus, water coming up with H plus and OH minus. So what will happen? Lithium hydroxide NH3, right? Even in this one, right? So this guy will come up with the M2 plus and the N3 minus. So if you have to come up with water, what will happen? Exchange of ions, MOH2 and the NH3. So the product produced by the reaction of metal with the ammonia will react with water to produce the ammonia again. That is the special thing here to grab, right? I'll write it here. The salt or product formed by reacting is metal with ammonia will react with water to produce ammonia again. That is special. See, if you're concerned, right, I write it here. If you're concerned the sodium NH2 solid with water, see, you have the Na plus here and the NH2 minus here. That will connect with the H plus and the OH minus appearing with the water. So Na plus and the OH minus will give you the NaOH, and H plus and the NH2 minus will give you the NH3 gas. See, NH3 gas is produced again. Let's come up with the magnesium nitrate thing as well. So magnesium, if it is react with ammonia as a group 2 element, will produce a nitride, right? The cations with greater porous power prefers anions with greater porous power, right? It will react with water. See the reaction. This can be considered as the connection of combination of Mg2 plus and the N3 minus. This can be considered as the combination of H plus and the OH minus. So what will happen? Mg2 plus react with the OH minus to form the MgOH2 plus the H plus connect with the N3 minus to form the NH3 gas. See, the product formed by the reaction of metal with the ammonia, these guys, will react with water again to form the ammonia. right? The clean things are clean. So complete this stuff as well now quickly at the page given there. At the page number 30, you can complete that stuff. Right now. Okay. So that is all for today. So we had discussed all the reactions involved in this block metals. Right. We had completed the reaction schemes where the block metals reacting with elemental diatomic gases, O2 gas, N2 gas, and H2 gas. And then we had discussed about how those guys will react with acids, H2O and NH3. All those reactions has been discussed, right? And then we had discussed about how the products formed by those reactions will react with H2O as well, with the kind of ion exchange reactions, right? So those are the reactions. Those are the basic reactions involved in the S block metals, right? Next day we'll discuss about the thermal decomposition reactions, not the um, not the reagent mixing, but the thermal decompositions. Next day we'll discuss about that thing and the precipitation reactions involved in the S block compounds. Right. Next day onwards we will discuss about more about the reactions with S block compounds, the thermal decompositions as well as the precipitations. Right. Okay. So from this we'll wind up for this today's session. Right. So until the next week we meet. Goodbye. See you next week.